All right.
And Natalie Butterfield is a postdoc at the Green Bank Observatory. She'll be talking with us this morning about high frequency corrections to the GBT.
Great, thanks, Will.
Thank you.
All right, let me know if my cursor shows up when I play this. No, I'm not seeing it. Okay. Let me see if there's a way that I can set this up. Okay. All right, in that case, let me just do single slide only. Let's see if we can zoom in, because there are a few places where I would want to show you all what I mean when I'm showing you some of like the Astrid screens and Astrid slides. So let's see. There we go. All right, so can you all see my cursor?
Yep.
Okay, perfect. All right, thanks, Will. So I am Natalie Butterfield. I am a postdoc here at GBO. I'm currently in my last year of my postdoc, so year 3, working at GBO. And this is my first postdoc after being a graduate student at the University of Iowa. And so today I'm going to tell you about high frequency GBT corrections. Oh gosh. Well, maybe I can't do it this way. Okay, well, we'll just have my side screen. Okay. All right, so the first half of the talk might seem a bit familiar. I think Dave covered this in his first talk that he gave on Monday, just going over some of the Gbt optics, but since it has been 2 days since we've covered this, I wanted to just reiterate some of the information there. And then the second half of the talk, I'll be showing you some auto OOF slides and the steps to go through and do high frequency corrections. So some of this might seem a bit familiar, but I wanted to cover it just because it will play in later on to the talk as well. So the Gbt Telescope Optics, so it's about 100-meter effective dish and is part of a 208-meter parent parabola. And so that's the figure that's shown here on the right, where you can see the Gbt parabola section along with the full virtual parabola of the parent paraboloid. So the Gbt is an off-axis instrument, so that means that it has a clear unblocked aperture, which helps reduce side lobes and allows us to produce some high dynamic range imaging. So in the talk that Dave gave on Monday, I think he showed a couple slides where you have like the VLA antennas and a few others. I think the Bond telescope also has a blocked aperture, so that means that you have these cables that basically help support the receiver cabin over the dish itself, whereas with the Gbt you see that you have this long sidearm, and that helps hold the receiver off, slightly off axis, and that allows you to have this unblocked aperture. And this seems to be the way that a lot of antennas are going nowadays. The NG-VLA, which is the next generation VLA, seems to have a similar design. So this seems to be the way that a lot of telescopes are going, just because it helps reduce side lobes and allows for your high dynamic range imaging. All right, so the Gbt has what's known as an active surface. So an active surface means that you have these little actuators. So that's what's shown here, in the oval. Is showing the actuators, which are positioned at the corners of each of the little plates. So on the previous slide here on the right, you kind of see all these little squares that make up the surface of the dish. And so at each one of those corners, you have these little actuators that help push or pull. And that's how you allow this active surface. So an active surface just means that your dish could be changing and can be changing to be giving you the best type of RMS or surface accuracy as possible. And so some of the issues that you could have with the surface accuracy could be coming from either just atmospheric defects that are coming in, or sagging of the dish if you're pointed low on the horizon, or just like heat. And so being able to have an active surface allows for us to be able to observe effectively at these higher. You have a very, very large dish. You almost really need to have this active surface in order to make this high frequency observations possible. So improvements to the active surface. So back in 2009, again, the telescope was commissioned in the early 2000s, but we made improvements to the active surface in 2009. And so on the top, you can see basically all those little panels. So this is showing you what this surface looks like across different months. So from January to September. And so you'll notice that starting in January, there were a lot of issues that we were having with the active surface. So there were some broken actuators. Those show up as being very hot spots or very dark spots. And those are just where the surface RMS was relatively poor. And so you'll notice that as we made those changes, the smoothness of the surface, or the RMS of the surface by September, looks relatively nice compared to what it looked like in January. And so the bottom panels are showing you what your beam pattern looks like for each one of those different months. And so as you can see, as you go further and further towards September, that the improved surface is causing a much better beam pattern that we can see in those bottom panels. And so this is just representing some of the improvements that we've made to the dish and how much improving the active surface or having an active surface can affect what your beam pattern is, even at some of the lower frequencies. So these were shown at almost 12 gigahertz. So even at 12 gigahertz, this can really make an improvement to the surface of the dish. All right, so this is another slide that Dave showed on Monday, but just to reiterate, so the GBT achieves its theoretical beam at 110 gigahertz. So this is up towards the Argus part of the range. And this is towards 3 millimeters. And so there's a nice GBT memo where we cover the success of the point and control system, which has some gravity and thermal modeling in the active surface correction. So gravity, again, if you're pointed low on the horizon, sometimes you can get sagging in the dish, and so you need to correct for that. Thermal modeling, so if you're changing from daytime to nighttime, sometimes the dish will relax, and so you need to be able to correct for those just deformations that you could be having in the dish surface. And so there's been a lot of work that's gone in over the past decade to be able to make these improvements. And so this just shows, the two figures here just show the theoretical beam at both 9 gigahertz, which is X-band, and at Argus, which is 110 gigahertz. Okay, so a surface with large random errors. So on the left, we're showing a figure which represents the receiver response. And then on the right is the surface errors. So this is projected onto an imaginary surface. And you'll see images that look like the one on the right here later on in the talk. This is actually a figure that you will get when you make an auto oof. So we'll go over those in a little bit more detail. But you should be seeing these again later on in the talk as well. And this is just representing the deformations or the changes that you have in the surface corrections. All right, so how do we do this modeling? So to do this modeling, we use what are known as Zerniky polynomials. So these polynomials are named after Fritz Zerniky, so the man who derived these back in 1934. And these derivations ended up winning him the Nobel Prize in 1953. And so these are essential for determining the beam optics. And so on the right, we're showing the patterns that you get for different Zerniky polynomials, along with a table with the different parameters for the Zerniky polynomials and the equations that go into them. So the Zerniky polynomials, we'll be seeing those later on. Typically, when we're doing our auto peak corrections or auto oofs, we'll be using Zerniky's polynomials 3, 4, and 5. So you'll see 3, 4, and 5 pop up a lot later on in the talk when I go through and show you the steps to do an auto oof. All right, but that's where they derive from. That's what the Z's mean, if you ever see this later on, that we're referring to the Zerniky polynomials. All right, so the Zerniky gravity model. So each Zerniky parameter is fit as a function of elevation. So as I mentioned earlier, you could have this sagging of the dish, especially if you're pointed low or if you have a low elevation source. So for me, I observe a lot of sources at the galactic center. So we point relatively low on the horizon. And so you can have a lot of sagging of the dish when you're pointed relatively low. And so you need to be able to fit for those changes that you have in elevation. And so the Zerniky gravity model is one way to do that. And so we updated the gravity model back in 2014 to improve the telescope performance. And so there is a note 76, where we go through and we have some additional details in there discussing the equation that's shown on the slide along with the table. But that's where that information came from. And we have additional information in there if this is something that you're interested in pursuing. Okay, so I think Dave also showed this slide earlier, but again, just to reiterate, so we have surface improvements using the Zerniky gravity model. And so in the figure that's in the top left, we're showing the different types of the relative efficiency that you have across different elevations. So elevation is shown on the x coordinate, and so you have your efficiency on the y coordinate. And so you'll notice that each of the dashed lines show different dates or different years. And so as I showed, I think a couple slides back, we made changes back in 2009 to improve the surface correction. So in 2003, so this was some of the initial modeling that we had when the first light or when the telescope came online. We made some corrections in 2009, and so you can see how much those improvements have helped fit some of the relative efficiency of the telescope. And then we've continued to make adjustments and improvements over the past 10 years or so. And that's how we are improving the efficiency of the telescope. So that's what that figure is showing, is just the improvements that we've made and how that has been improving our efficiency for the telescope, at least at 43 gigahertz, which is shown here. We also show in the top right, so this is similar, but this is for 80 gigahertz. So we're also improving our efficiency at 80 gigahertz by including some of these gravity models in our when we're doing our surface corrections. The bottom right panel is the surface errors. So as we have fixed some of those broken actuators, which I had shown earlier a couple slides back, we've improved what the surface RMS is. We've continued to make those improvements. So as you've made those improvements to the surface RMS and lowered those surface errors, we've improved the efficiency of the telescope. And so that's what these figures are showing, is how the telescope has improved over the past few years and how the surface errors and RMS has decreased over the past 10 years as well. All right, so improvements with the Zerniky gravity model. So continue on with this. So the Zerniky parameters depend strongly on both the gravity and the thermal corrections of the antenna. And so these can require real-time corrections to the gravity model as well. So the total Zerniky corrections that you need to make are both gravity, or include both gravity and thermal corrections. So as I had mentioned, these thermal corrections basically come from either heating of the dish, or where you have these changes or deformations from if you're going from daytime to nighttime observing, you can have the dish start to relax as it starts to, as the air starts to cool off. And so you need to be able to make these corrections real time in order to improve the surface RMS or accuracy and efficiency of the instrument. Okay, so now getting into the auto OOF. So the OOF stands for the out of focus mapping. So this is where you have observations of a bright source, and you use that bright source observations to derive the Zerniky parameters. So typically you take 3 observations. So you have one where your observations are taken in focus, and then you're slightly out of focus in one direction and then slightly out of focus in the other direction. And so that focus deviations are how you can help derive your Zerniky parameters. So we'll be going over those in a little bit more detail later on. But essentially, when you're doing an auto oof, these are the 3 different images or maps that you will be making. So you'll be making one in focus, one out of focus in one direction, one out of focus in the other. And so that's why you see this minus VE and plus VE, is that they are going in different directions of the focus. Okay. All right, so getting into an example of an Argus auto oof observation. So the first scans that you will be taking, so scans 1 and 2, are your vane cal scans, which are taken with the DCR. So the first scan is taken with the vane, and then your second scan is on the sky. And so typically your system temperature is the variation that you have between the vane and the sky, which under good conditions is usually about a factor of 3. So those will be the first 2 scans that it will take whenever you do a auto correction for high frequency observations. All right, so then the next one, so scan 3. So this is where you will be taking your first map of your auto oof. All right, so as I had mentioned 2 slides back, you take one in focus, one slightly out of focus in one direction, one slightly out of focus in the other direction. So this is the first scan that you'll be taking. So this is default in focus, and you should be able to see good signal to noise in this observation. What you'll notice is that you have these very nice peaks relative to relatively low noise, and that's the sign that you're taking, that you're looking at a bright source. You want to make sure that you have a bright source in order to make a good auto oof solution. And so I'll be showing a couple examples later on in the talk of good solutions and bad solutions, and solutions if you or what solutions will look like if you don't have a bright source. All right, so this is an example of a good signal to noise of what your first scan should be looking like. And again, at the very bottom, you'll have, it will tell you which part of your map that you're in. So right now we're in oof map 1. All right, so next one, again, oof map 2. So now we're at our second map that we're taking. And so this is made slightly out of focus, so plus 12 millimeters. So you'll notice that your signal to noise goes down a little bit. The data doesn't quite look as well, but again, we are slightly out of focus for this scan. All right, and then the next one is, again, where we are slightly out of focus, but we're at minus 12 millimeters. And so for this one, the peaks are slightly higher than at the plus 12 millimeter map. But it's still not as great as what the solutions look like when we were in focus. So again, just to walk through these. So this is in focus. This is plus 12 millimeters out of focus, minus 12 millimeters out of focus. So you'll be making 3 maps. Typically, these maps are about 5 minutes or so, a little bit over 5 minutes. And so in order to do a full auto oof correction, we suggest that people account for roughly 20 to 30 minutes overhead for each auto oof that they will be making in their observation. So if you're applying for telescope time, we suggest that you have at least 20 to 30 minutes budgeted for an auto oof if you're including that in your observations. So they each take about 5 minutes, and then you need to have time in order to analyze your solutions or make another auto oof if your solutions don't look great, or if you have a faint source and you need to find a brighter source. Okay, so now what do these look like when they are being processed? All right, so you've taken your 3 maps, it's gone through and done these calibrations, and it's made solutions for your Zerniky polynomials. All right, and so this is what you will see in your OOF tab once you have completed an auto OOF routine. So what do these show? Okay, so you have your different Zerniky solutions. So as I mentioned, previous, we had Z3, Z4, C5, and I mentioned that those would pop up later. So that's what each of these are showing. So as you click on different types of Zerniky solutions, it will show you what your map will look like for each one of those different solutions. At the bottom of your map, it will show you what the surface RMS is. And again, these will change depending on which solution you've selected. So you will see some either slight, or you could see potentially major changes in your surface RMS depending on which solution you have selected. The default that comes off the telescope, so when this pops up on your screen, the default is always Z5, but you do want to check what the other solutions look like. Don't just blindly select the default Z5 and send those without actually rigorously checking what the solutions look like, checking your raw data and checking your fitted beam map data. And I'll show those later. So for your, so a good solution, typically the surface RMS, you want those to be relatively low. So anything that happens to have a very large surface RMS, so something above 350 microns, you don't want to be using those solutions or passing on those solutions. Typically those happen if you have either maybe windy conditions. So if the telescope or the feed arm is shaking, if it's windy, then that can affect what your solutions look like. And so if you have a very large RMS, you do not want to be sending those solutions to the telescope, because it will make changes to fit that RMS. And so if the RMS doesn't look good, then that can affect what your beam solutions look like and the solutions that you're getting from the telescope or passing to the telescope. Okay, as I mentioned, okay, we looked at what some of the Zerniky solutions or maps look like for the telescope. So raw data. So if you select raw data in your OOF, you'll see a screen that looks like this. So what these are showing you is both the solutions that we were looking at earlier. So how we did in focus, slightly out of focus in one direction, slightly out of focus in the other direction. And so this basically will just show you what the raw data looks like as a summary of each one of those different mapping scans that you would take in. And then down here, it will show you some of the observed beams, but I will talk about those in the next slide because you'll have a few other options if you click on this fitted beam map. So you click on fitted beam map, and then you will get basically a summary of what your beams look like for different Zerniky solutions. So up here, you'll see that it has Z equals 3 fit, Z equals 4 fit, Z equals 5 fit. And so this is basically showing you across each row what the focus, slightly out of focus in one direction, slightly out of focus in the other direction look like for each different Zerniky solution. And so these are relatively nice solutions. All of the beams look relatively uniform circular. You're not really seeing any type of molted or striping patterns or anything like that. So all of these solutions look relatively nice, but I will show you a couple slides later on what some bad solutions will look like. But that's just a summary of what the different buttons are in an auto OOF in Astrid. Okay, so let's say, for example, you're happy with Z5 and you want to pass that on to the telescope. You would select send selected solution with point and focus corrections to the telescope. And so it would send those corrections to the telescope. And so that would be how you would accept and be able to pass on those solutions. Okay, so now let's take a look at what some poor solutions would look like. All right, so we saw earlier, this is an example of, a fairly nice solution. You have bright signal to noise. Your beams look relatively circular. Those all look great. And then on the right, we're showing a poor solution. So this is what you would see if you had a relatively faint source. So you'll notice that the signal to noise, even in focus, is relatively low. And again, that's signature that you don't really have a very bright point source. So your signal to your noise level is low. And then your observed beam patterns look relatively molted. And again, that's just because your source isn't super bright. So in this case, you might want to find a nearby brighter source that you can use, or you could always go down to maybe a lower frequency where the source is relatively brighter. So just because you're observing at Argus or with Argus doesn't necessarily mean that you have to take your auto OOF with Argus. If Ka band, which is 36 gigahertz is on the instrument, then maybe you want to drop down to a lower frequency to do your auto OOF solutions or corrections using that receiver. So just because you're using Argus doesn't necessarily mean that you have to take your OOF corrections with Argus. You could always go to a lower frequency depending on what receivers are on the telescope at that time. So you don't want to go anything lower than K band or so, but Ka, Q band, those would be fine to do your OOF solutions as well. Okay, so an example of a bad OOF solution. So a couple slides back, we showed a relatively nice OOF solution. Actually, I think I might have skipped a slide. Okay, so OOF solutions, so a relatively acceptable versus unacceptable OOF solution. So in this case, what we have is the on the left here, we're showing a relatively nice acceptable OOF solution. So in this case, we're seeing minor variation across the dish. We're not seeing any very large or steep gradients. And so this is an example of a nice OOF solution. Again, we have relatively low surface RMS. However, on the right, this is an example of what a poor OOF solution or an unacceptable OOF solution would look like. So in this case, we had relatively high surface RMS, so around 600 microns. We're seeing very steep gradients across the dish structure. And so you would not want to use any OOF solution that looks something like this. And again, maybe this is just in one Zerniky solution. Maybe some of the other lower Zerniky polynomials look better. So this is one of the reasons why you want to have time to be able to look through those different solutions and be able to determine which ones you want to be passing on to the telescope. So don't just go with the default of Z5. You want to actually look through your different Zerniky solutions and select the ones that look acceptable. Okay. So an example of a bad OOF solution. So in this case, this example here was an observation that was done in the keyhole. So the keyhole means that you are basically almost pointed directly up, and the telescope isn't able to track fast enough to follow your source. And so you ended up having a very large surface RMS, which in this case is over 400. And you have a very large focus and elevation pointing offset as well. And so again, this is the one for the default. So Z5. So just because it defaults to Z5 doesn't necessarily mean that is the best or even the one that you want to be passing on. So again, you want to check the raw data and check the fitted maps and look at the different solutions before you click this button. Okay, so I just want to make sure that we stress that you do look through your data, that you check your different solutions, you check the raw data, you check your fitted beam map, and then select the one that looks the best to pass that on. All right, so this is for the same exact example. So again, we're just following an example through. So when you click on the fitted beam map for these observations, you'll notice that you have these streaking patterns in your observed beams in focus. And so you'll notice that you can't really trust these results. So the observed beams mean that that is what your point source would look like if you passed on these solutions to the telescope. So anything that you take, any observations that you take with these corrections, this is what your point source or your beams would look like when you take your observations. So that is one of the reasons why you want to make sure that these look relatively circular, and that's a sign that you will be taking relatively good data, or at least you'll have a relatively good surface to be taking your data with, okay? So anything that looks like this, you do not want to be passing on to the telescope. All right, here's another example. And in this case, there's just one Zerniky solution that looks bad. So as I mentioned, just because one or two look fine doesn't mean that they all will look fine. And in this case, it's the Z3 fit that you do not want to be using this solution. So for Z4, Z5, these look relatively circular. The solutions look relatively nice. But at Z3, you're seeing this really wide streaking pattern. And so in this case, you would not want to be passing the Z3 solution, but Z4 and Z5 look fine. Okay, so anything that looks like this, you do not want to be selecting that solution to be passing on to the telescope. All right, so this Clio status window. So I think we've covered some of the Clio windows, either in your observations that you guys took 2 nights ago, or in Breen and Amber's talk when they went over Astrid and Clio. So a lot of these will look familiar, but the one that I really want to draw attention to is your active surface. So again, if you're doing your active surface corrections and you're using OOF, you want to make sure that your active surface is on, and that you have passed your solutions to the telescope. And that will be found under devices and under the active surface. So you might have to slide over. You'll notice that you have this, bar down here. So you might need to move over to be able to see the active surface window or information, but it will be under the devices tab. Okay, so if you want to make sure that it's on, you want to make sure that they're there. This is how you will find that information. Okay, so just some observing strategies. So I mentioned that it takes about 30 minutes or so to do or we recommend that you budget about 30 minutes to do an auto peak focus and auto OOF. The OOF itself takes a little over about 20 minutes, roughly 20 minutes or so. It's about 5 minutes for each one of those maps. And then you would need time to be able to look through your solutions and send the correct solution. So we suggest that people budget about 20 minutes or so for the OOF at least. And then so combining that with your point and focus, your auto peak focus, you might need to be doing those every 30 to 50 minutes. OOF takes about 20 minutes. And we suggest that for your OOF, depending on when your observations are taken, so say for example you're observing from let's say 7 or 8 p.m. up to maybe 11 p.m. Where you're crossing in from dusk, and so maybe it's warmer when you start your observations and then it starts to cool off since it's going to nighttime, that you might want to start taking your OOF corrections a bit more regularly at the very beginning of your observations, just because you're going to be having some thermal changes as the telescope cools off. So typically a good rough estimate is about an hour and a half, 2 hours, but it really just depends on how long you have for your observing session and when your observing sessions are taking place. So if you're observing in the middle of the evening and you only have maybe an hour or two on your telescope time, and let's say for example that you don't really worry too much about the point source or how compact your point sources are, then I think you should be fine with just having one at the very beginning of your observations. But if you want to do it every hour or every hour and a half, I think that's fine too. It just depends on how much overhead you've budgeted versus how much time on source, because you don't want to spend all of your time doing the auto peak focus, the auto oof, and then really not be able to get the science that you're trying to do and spend all of your time doing these calibrations. So you just want to make sure that you are planning out your observations and when you want to be doing your auto oof and when you would need to be doing your auto oof. So definitely at the very beginning of your observations, if you're doing high frequency and you want to have the best point source solutions or the best beams in your observations, then you want to be doing your auto oof at the very beginning of your observations after you've done your auto peak focus. But then you might want to think about how long your observations are and when you might need to be making your second or third auto oof solutions throughout your observing run. But those are just some basic observing strategies. And if you guys have any questions, your project friend or, we are here to help you with any questions you have, if you are concerned about when you might need to be running these. All right, so just another thing that you will want to be doing to do high frequency corrections. Again, this isn't related to the auto oof, but is something that you will want to make sure that you have listed when you start your observations, or that you make sure that you update when you start your observations at high frequency. The default when you do observations is standard. So under heuristics, so this is options in Astrid, and then you will see a window that looks like this. If you click on heuristics, you'll notice that it will default to standard. And so you want to make sure that you have your heuristics set to be relaxed for high frequency observations. So anything that's above about 20 gigahertz or so. And we can cover this in the observing runs tonight if anyone is doing high frequency or wants to do high frequency and they're unsure of where to find this. Let us know, or we can go through and show you where you can find these. You will need to make sure that you select it for pointing and for focus. So just because you change it for pointing does not mean that it will change for focus. So you will need to do this twice to make sure that you've changed it from standard to relax in both pointing and your focus tab. All right, so lastly, with the last little bit of my time, I want to cover a new instrument that we are currently adding to the telescope that's known as Lassie. So Lassie is a terrestrial laser scanner, and basically it sits up near the receiver cabin and will be scanning the dish. And the reason why we are pursuing this avenue is to allow and open up more daytime observing for high frequency. So for high frequency daytime observing really isn't that feasible at the moment, just because you have so many thermal changes that are happening constantly that you would almost need to constantly be running an auto oof and therefore not have any time to do your science. And so that was a real major push behind including Lassie, or pursuing Lassie, was to be able to scan the surface much more quickly. So it only takes about 6 minutes to scan instead of the 20 to 30 minutes that you would need for an auto oof. And so by having less time spent overhead, we should be able to pursue more high frequency observing during the daytime. And so this is just a schematic here on the right showing what Lassie would look like with it scanning the surface. All right, so we have been doing some testing with Lassie. And here's a photo showing the Lassie instrument installed on the GBT. So as I said, it sits above the receiver cabin so that it can look out over the dish and be able to scan the primary surface and be able to make corrections real time with those actuators and being able to fix the surface corrections. All right, and so here's one of the pictures that Pedro Salas, who is one of the postdocs that is working on the Lassie project, sent me with some of their initial scans that they've been doing and some of the testing that they've been doing using Lassie, just to show what the images will look like from the instrument. So this is currently a work in progress. Pedro might be able to add in the chat if they have an ETA. If it's, I think it's in the next year or two, I think they're hoping to have it installed, and being able to use for some high frequency corrections. But I wanted to include it in the talk on high frequency corrections because it will be coming online in the upcoming years. So we don't have it on there right now. We don't have it open for users right now, but it is something that within the next couple of years, you should be able to see that online. So I will stop my talk there and I think take any questions. I think I saw a couple show up in the chat window while I was giving the talk.
Yep, the most recent one is, if you think the OOF values you are getting are borderline acceptable, is this something you can ask the operator to look at and give an opinion?
So the operators, I think it's something that if it's borderline and you're unsure, that would fall more towards either the on-call scientist, since they are trained to be able to look at OOF solutions and be able to be trained to give feedback on the science. The operators, I think that's a little bit outside of their area of expertise at the moment. I don't think that is currently in their like in their job description as being able to judge science or be able to say, yeah, that looks fine, and have that be acceptable. I think that's something that would almost fall to the on-call support scientist to make that call. So.
Can I add, Natalie, that if you have an Argus program, you will be observing with your project friend or with an Argus scientist for your first run at least. So you'll get some experience with a scientist before being thrown into the deep end.
Yes. Okay, any other questions? Okay.
Dave put a little bit of clarification in there, suggesting that if KA is available, you should use KA to OOF. And then there was a question about what the surface RMS is. So we put some clarification in there. One thing that I wanted to ask is, I believe with a recent Astrid update, you don't have to manually relax the heuristics anymore.
Okay.
Is that true?
That's correct.
Okay.
That was deployed actually this spring, earlier January, I think it was. So yeah, so what we have now, there's a default. Bryn mentioned this, I think, in her presentation earlier. If the frequency is above 27 gigahertz, meaning Ka and above, the software system will automatically, this slide's out of date because we have a default button now. It will automatically use the relaxed heuristics at high frequency, and then at lower frequency you'll use standard heuristics. It's still a useful point because the cutoff is Ka band and above. We have the highest frequency we're observing at this workshop is the KFPA, which is below that cutoff. The weather is going to be marginal tonight, so users who use the K band should choose relaxed heuristics for both their pointing and focus. So this information here is helpful because we'll need to do that. Typically, you wouldn't be scheduled for K-band tonight, and just the defaults would work. But since we're going to probably take observations in less than ideal weather for training purposes, we should relax heuristics tonight for both pointing and focus for K-band observations.
Yep. Any other questions?
I don't see any.
Okay. All right. I'm going to stop sharing.
Okay. Thank you very much, Natalie. Our next talk and the final talk of this morning session will be done pre-recorded. So we will have Tony Minter telling us about the dynamic scheduling system, and then we will be on hand for any questions after that presentation. So I will share that, but I'm also going to share directly the link to that. The GBT, as we've talked about, is what we call dynamically scheduled. So in the old days, you would be given a block of time where you would come to the observatory, and you would have maybe 2 weeks in that time to do your observations. Now we schedule the GBT based on the weather. So if there is a really clear night and not much water vapor in the atmosphere, we will schedule Argus observations. If the weather is a bit more marginal, we will schedule L-band or pulsar observations. And so we do this scheduling 2 days in advance, which does not give, which gives us the best chance to predict what the weather will actually be those nights. So the system that we use for this is called the dynamic scheduler, and Tony Minter will tell us a little bit about that now. Let's see, can you see the video?
Yes, Will.
Great.
GBT has a huge range of observing frequencies, all the way from 100 megahertz up to 115 gigahertz. And that's an incredible energy range. That's, basically bigger energy range difference than all of the NASA great observatories put together. So it really does affect how we have to consider scheduling the telescope, because at the highest frequencies, you need the best weather, especially if you're doing Mustang or continuum work. And at the lower frequencies, the weather really doesn't matter for the most part. And so the dynamic scheduling system is what we use to schedule GBT. The basic goal is that we schedule the telescope 24 to 48 hours in advance. Why such short notice? Well, because the weather predictions still are only good out to about 3 days. So try to forecast things further out. It's really difficult, and you wind up scheduling things at inappropriate times. The weather changes on you from the forecast. And so 24 to 48 hours in advance gives people notice so that they can prepare for their observations, but we can still be fairly certain that we know what the weather conditions will be. It's sort of a balance between those two. And this also allows us to maximize the use of the excellent high frequency weather when it does come through. Now, various things that do matter for the weather concerning the observations with the GBT or water vapor. Of course, there's the 22 gigahertz line of water that if you have too much water vapor, you just can't see through the atmosphere. And that line does affect a good range of frequencies. It's a really broad line. It can affect up to things 10, 20 gigahertz away from that water line can be affected. Aerosols are also important. These are the other things like soot, dust that are in the atmosphere, other chemical elements that do have refractory properties for radio waves. They can become really important at the highest frequencies, up around 900 gigahertz. They can be the dominant thing. Then we also have to consider whether it's clear or cloudy. If it's cloudy, we could still do spectral line observations, because there you're switching fast enough that the clouds are taken out by the, you can handle that with the switching that you're doing. But if you're doing continuum work, you really need to be clear, because as a cloud goes through, it's hard to remove that from the data. So whether you're doing continuum or spectral line really can matter on whether it's clear or cloudy, even though the opacity might be great in both conditions. You can have a thin layer of clouds. We get that quite often from temperature inversions that are great for spectral line work. You wouldn't see the sun. You wouldn't think it was great high frequency weather, but it really is, because there's a thin layer of clouds that's out there. Also, whether the clouds are composed of water vapor or ice can make a huge difference. I've actually been through a observing scenario where we couldn't see the signal from a spacecraft at 13 gigahertz. And then all of a sudden the signal comes whopping in. We look out and the weather had changed from pouring the rain to very heavy snow. And just that quick switch from, you know, the rain being water to snow being ice suddenly greatly increase the, or decrease, I should say, the opacity of atmosphere. And we could suddenly see that satellite very brightly. So whether the clouds are water or ice can really matter. And as we just heard, winds are a factor as they can blow the feed arm around. Basically, the wind, if the telescope's a big sail, the wind does move the telescope around. The net result is it ends up causing small vibrations in the feed arm. And either the wind's too strong, it can blow your source, blow the telescope off source and you can't stay on source. Or those little vibrations can be enough that the calibration of your data becomes more uncertain than 10% or so. So we do have wind limits calculated from that. There is hope in the future. This is a project that's way out, that we'd be able to use a device on the telescope to see how the feed arm's shaking and then use the subreflector to counteract that. But that's a project that hasn't gained any footing yet, but it might be possible to make the wind limits higher sometime in the future. Now, so the dynamic scheduling system can be quite complex because the different factors that go into the weather and everything. And so we do provide a rough idea of what the observing conditions will be at all the different frequencies that we can cover. This is a grab from its nicknamed the pizza plots. They're available through the DSS system. And they basically give you an idea of where it's good to observe. So green is good, blue is okay, and red is bad. So you can see that compared to the best conditions that we do get, last night was fairly, our Monday night was fairly good for the high frequencies all the way up to 115 gigahertz. However, we do have a system coming through a little bit later today, this morning. It's mostly clouds. Then you see a little bit of good weather coming up tonight, and then we'll have a storm coming through, and there's a lot of red on the system. Now, typically observations below 10 gigahertz, it really doesn't, the difference between it being green and red doesn't really matter. But as you get up to higher frequencies, it really can matter. And then, you know, around 22 gigahertz, you can see where the water vapor line rarely moves away from red. And this will be an important point for people observing ammonia or other lines besides the water vapor line. You really want to make sure that your frequency is offset from that water vapor line if it can be in the dynamic scheduling system, because it can make the difference between your project being considered for scheduling or not. So the DSS is located at this website, dss.gb.nrio.edu. You go to it. That's what the page looks like for you to log in. You use the exact same button to register for a proposal submission tool, PST account. DSS uses the exact same username and password as the proposal submission tool. Now, these are different usernames and passwords than you would use to log into the computers on your Linux or Windows account in Green Bank. So these are completely different systems. So remember to keep those different. And pardon me just 1 minute. Sorry about that, folks. All right, so moving on, once you do log in, this is what your page will look like. You go to your own personal DSS page, and in that, you'll see a list of useful links up at the top. And we'll just go through those real quick. So you can see what the GBT schedule currently is by going to the GBT schedule link. The weather forecast, like the pizza plot that I showed you, is available under the weather links. If you want to submit an observer comment to us, there's the observer comments link. You can submit help desk tickets or look at the documentation under the help. And also, if you hit the home from any other place in there, that brings you back to your own personal page, like shown for me here. Then there's the normal log out button for the DSS. Now, important one to know is your preferences. That's right under your name on the DSS page. You can go in there, change contact information so operators know where to reach you, or we know how to email you to let you know your project's been scheduled. Things like that are in preferences. Then a list of all your active projects is right below that. And then all your upcoming scheduled observations will be over here on the right. Typically that shows up on the right, but sometimes the way depending on font size and other factors in your browser, this section for upcoming observations can appear at the very bottom of the page instead of over on the right side. So just be aware of that. And if you want to, you can create an iCal link from the GBT observing schedule to appear on your favorite schedule. So that does work on getting it onto things like Google Calendar and other calendars. It makes it kind of easy to keep up with things. So now if we go on and scroll down the page, look something like this. So below the upcoming observations, you have a list of reservations that you might have coming up. The scheduling system does give a boost if someone's visiting the Green Bank site. Unfortunately, you can't currently do that under the current COVID situation. But under normal times, when you would possibly come visit Green Bank, you do get a boost in your chance of being scheduled. And any reservations should show up over on this site. If your reservation doesn't show up, then you should contact your project friend or myself, let us know, and we can try to fix that situation. You also have your contact information. This is how we, again, are able to contact you to let you know you're scheduled, or if operator needs to get in touch with you during your observations. And you just use this link that's right there to update your contact information. That's actually in the proposal submission tool, where that information is stored and updated, and it's automatically propagated into the DSS. Now, if you want to update any of your dynamic contact information, this is a text field like, hey, I'm going to be at the neighbor's party and here's their number for tonight. You can put that information there. It's not necessarily permanent information, but special information under certain circumstances can go in that text field. And you want to make sure that you keep your contact information up to date, because this is how we will contact you. There's literally 10,000 people in this database, so we can't go in and expect to have people say, please update my email to this. It's just too many people for us to keep track of it, so it falls upon our users to make sure that they keep the contact information up to date. And then down below, you'll see any projects that have completed or been closed on the telescope will show up down here under completed projects. And those won't be considered for scheduling, but you might need to know what these project numbers were in case you need to go get the data out of the archives or anything to see what you've done in the past that might affect what you're doing in the future. Now, you do have the ability to enter times when you're not available to observe on the telescope. That's in this section here. And so you just click add right there to enter a time range when you are not available to observe. And when you do that, you get a page that looks quite like this. One thing to note is that you can only repeat these not available to observe dates on a weekly or monthly basis. You can't repeat them on daily. So if you have a daily time when you can't observe, you're going to have to enter, 5 to 7, depending on whether it's just weekdays or the whole week, those times, and then you could have them repeat weekly or monthly after that, but there's no daily option, unfortunately. So, and then one bit of warning here: if you have many repeating short periods of time when you can't observe, these can actually be a significant barrier to keep you from being scheduled on the telescope. We actually had one person who put in a daily choir practice, and they had a very long observing block for when they would be scheduled. And any time that you can't observe time periods overlap with your can be scheduled time periods, then we can't schedule you unless we can move that schedule period outside of when you can observe. And in this case, this one person's choir practice literally knocked them out of 7 or 8 months of the year when they couldn't observe it. So you really want to be careful of how your observing LSTs do overlap with the periods when you can't observe. So going on down, let's actually go look at one of the project web pages. This is where most of the action that you'll be concerned with will happen. Here's one such project page, one that I was on. Every project on the GBT does get assigned a project friend. This is a local expert who can help you out with any problems, starting from the time your proposal is accepted up through the time that your paper is published. Please feel free to contact the project friend with help that you might need, setting up observations, reducing data after an observation, and so forth. Now, we do have on-call friends who will be different than the project friend, who will help you with the actual observations. And the reason we do that is we can guarantee that an on-call person is always available, whereas the project friend might have to have gone to the grocery store to pick up groceries or be on vacation and might not be able to help with the project when it's scheduled. So the on-call friend picks up those responsibilities for the actual observations. We do take into account if it's a student's thesis project or not. This is indicated by this thesis section. How much time you've been allocated by the time allocation committee is shown here under total time. How much time the project has been has currently observed is under time billed, and whether the project's complete or not is also shown there. And then you have an indication of whether the receivers are available for your project. But just beware that this uses an OR logic. So if your project needs the 800 megahertz feed and the L-band receiver at the same time, you'll probably never see the times that the 800 megahertz feed's not available on the telescope because of this OR logic, because one of the receivers that you need is available. However, if none of the receivers that you need are available, they will show up here under the receivers unavailable time period. So it gives you some indication, but not a bulletproof view of when you can and can't be scheduled because of receivers. And then if any project team member is visiting the site, then this will show up in upcoming reservations on the project page. Now, the sessions are what will be scheduled on the telescope, so it's important to pay attention to these because this is all the parameters that we're using to schedule your project are mostly shown here. Each session will have a name. It's usually your project ID followed by some sequential number. The right ascension and declination that are assigned to a project is what's used to schedule the session. And if this right ascension and declination is not up, your session can't be scheduled. And so typically the DSS, if you have many sources or more than one really, will average those right ascension and declinations together and use that average value. In some cases, this works just fine. In others, it might not be what you need if you have other LST restrictions and everything. So you need to make sure that the RA and deck used in this session is up and available during all times when you think your schedule should be, or when your session could be scheduled. The frequency that's listed here is what's used back in more or less that pizza plot to determine whether your project can be scheduled or not. So, it's important here that if you're observing, say, the ammonia line at 24-ish gigahertz, they'd want 24 gigahertz here rather than 22 on the water line. Because as you saw from those pizza plots earlier on, we could observe ammonia quite effectively, but not so much the water line. So it really is important to make sure you have the right frequency listed here for the science that you're carrying out. Then you'll have the receivers listed. Now this will use both and or logic for the receivers. So if it's and logic, then all the receivers listed need to be available. If it's or logic, just one of those receivers needs to be available for your project to be considered for scheduling. Then for each session, we have the time billed and the time allocated listed. This is different from what was over on the right side, which is the total project time. This is the time just for each session. The minimum, maximum requested lengths of time that you can be scheduled on the telescope are listed here. Once you do start running down time, I will automatically drop the end time, how much time's left on the project if it's less than the maximum length. But you might need to change these parameters for other reasons. So just contact me if they don't look right to you and I can fix those. Then the type of project can really matter. Like I said, whether you can, if it's a high frequency day, but with the thin layer clouds, you can't do continuum. So that type between spectral line and continuum can really matter. Other types are pulsar, VLBI, and radar. And there's a few others, but those 5 cover the vast majority of observations. Then you'll see the priority that each session has been assigned. It can be A, B, or C. A priority is considered first for scheduling, then B, and then C. All right, you have to be able to consider a session for scheduling. There's 2 things that need to be met. One, you have to check the enabled box, and also you have to have an observer available. We'll get to that in a little bit. And so if you don't see a check in this enabled box, that session will not be considered for scheduling. And you really want to make sure that you do have scripts ready to go before you do check a session for enabling, simply because there is a short amount of time between when you do get scheduled and when you will observe. And if you don't have your scripts at least starting to be prepared and your project friends on vacation, you might not be able to get those scripts done in time for your observation. So you really want to try your best. Make sure your scripts are done or are far enough along that checking the enable box means you could observe the next day more or less. There are other parameters that can control the scheduling of a project, and they'll show up here. These are not set by default, so that's why they come under other. And you do have to request that those get set by myself. This is not something that a project friend or you can do. So some projects you need a minimum time in hours between scheduled sessions. So you're doing some sort of monitoring, or you need to make sure that you have enough time to reduce the data and looking in a new technique possibly, or something like that. So we can set those times. The default is 0. There's the chi factor, which allows you for being considered for scheduling in worse weather conditions. So the default is this value is 1. We do use 1.1 or 1.2, can be commonly used. An example of when this might be the case, let's go back to that water line. If you're looking at very strong water mazer, then you can actually observe in weaker conditions. And so you could go with a higher chi factor and get scheduled in a little bit worse weather, because your mazer is so strong, the weather doesn't matter as much. And then you can have LST exclusions and inclusions to restrict when you're going to be scheduled in terms of LST. Now, the reason we do exclusion and inclusion is that it's hard to get things to go across that 0-24-hour boundary in the same way. So if you do go across that boundary, we use the exclusion, the part that still stays within 0-24, and then it allows us to get across that boundary in a sane and simple fashion, programming wise. Source size can matter. If you have a very extended source and you're just going for spectral line detection within that source, then you can put in a bigger source size, which means you can observe at higher winds, that even as the telescope beam is buffered around because the feed arm's shaking, it stays on the source that in a little higher wind conditions. So it might be appropriate for you to request a certain source size. There's also what's called the tracking error threshold. And this is how much jitter from the wind you can tolerate and still get calibration that meets your needs. The default is that the calibration error is less than 10% from the winds for any receiver, and this varies by receiver. I can't tell you the numbers quite off the top of my head, but at higher frequencies, you can withstand less wind than at low frequencies, just because the beam sizes are so much smaller. There's an elevation limit, so your observations must be scheduled above that limit. Each receiver has its own default, but you might have reasons to go below that default. Typically, say for 100 gigahertz, the default is going to be 30 degrees, simply because that's where you start hitting 2 atmospheres that you're going through. While pulsar observation might want to, go down all the way to the telescope's lowest limit of 5 degrees, simply because there you're observing at low frequencies and the atmosphere matters much, much less. All right, irradiance is another factor that's primarily for continuum observing. So it's looking at the upward versus downward infrared flux. It gives you some slight sensitivity to cloud cover, but it's mostly the atmospheric temperature that's primarily sensitive to. But it is an indication of whether things are good for continuum observations or not. There's also solar avoidance. If you're observing at L-band and get near the sun's radio emission can start having an effect on your baselines. So you might need to have some avoidance of the sun. The default is 0. I will tell you that GBT can look directly at the sun all day long, even on a sunny day. It has a special reflective paint that sends the optical and infrared light scattered around so it doesn't get to the focus. And the temperature at the focus, we've actually put a thermometer there. Looked at the sun on a bright sunny day. It only went up 1 or 2 degrees Kelvin. So we can observe the sun all day long without damaging any equipment or melting anything. Time of day might be important. So we have our standard night definition, sunset to sunrise. Some observations need to be done when the sun's not up because it can interfere with those observations. So then we have the Rfi Night Definition, which is roughly 10 p.m. to 6 a.m. This is when use of, people go to sleep and stop using their devices. So the RFI situation can actually be a little bit cleaner between 10 p.m. and 6 a.m. And then we have the thermal night, which is used for the highest frequencies. And this is when the telescope structure is most thermally stable and not changing very much. And it goes from 3 hours to around sunrise. Depending on conditions, this can actually extend a couple hours past sunrise. Then if you need to observe your source by its transiting, such as a polarization, calibration, observation, then we do have a flag for making sure that the source transits during the observation. Since the GBT is an alt-azimuth, there are places near the zenith where the source moves through the sky faster than the telescope can move to keep up with it. This is called the keyhole. If your source happens to pass through it, so it's at a declination that's near the latitude of the GBT, which is roughly 38 degrees north, then you might consider having this keyhole parameter set, because the telescope will not be able to keep up with your source as it gets near the zenith. All right, going back to our project page and moving on down a little bit further, you'll see upcoming observations over here on the right. They'll tell you the times and which sessions are scheduled for any upcoming observations. There is a calendar which shows you times when you can't observe, times when your project can't be considered for scheduling for other reasons, such as something else is already scheduled, or we have a maintenance day, so your project can't be scheduled. Will all show up on this. It also shows you times when you are scheduled for observing. So these gray areas down here are times when you couldn't be scheduled, so that conflicts with maintenance. Times when you can't observe will show up in the green, and times when you're scheduled will show up in the blue, light blue here. All right, going further down the page, you'll have a list of all your project team members. This can be include more people than are on the proposal. If you say gather a student later on, or another person joins the project, we can happily add those people on as a project team member in the DSS. Each team member has a contact email that's used when the project's scheduled. There's a column to note which person is the PI for the project and who the should be contacted in case we need to contact the project team. There's a column for whether you're remote qualified or not. And then there's the observer's checkbox, the other condition needed to make sure that your project can be scheduled. Remember, the session needs to be checked that it's enabled, and you must have at least one observer. If you're not going to be on site, that observer needs to be remotely qualified for you to be considered for scheduling. Then you'll have your project friend will be listed. In some unusual cases, you might have more than one project friend. It doesn't happen often, but you'll see your project friend's email. And then in unusual circumstances like extreme setups that require expertise that you might not have, we will require the project friend to be available for the observations. So there are times when they can't observe will be taken into account in scheduling the project. This is something that I have to set in the system, and that would show up as a checkbox in the required field, and we would have that checked. That's rarely the case for most projects. Then you'll see a list of times when people can't observe that shows up below that and gives the time ranges. And there's another feature which is called project blackouts. So if we go back, so these observer blackouts, as long as one observer is available, then the project can be scheduled. But for the project version, the whole project has to be available to be scheduled. So this is a yes, no on the project rather than the observer being a maybe. It's the way to think about it. So if the project can't observe, then the project can't be scheduled, period. So This can be used for certain monitoring observations that aren't guaranteed specific periods on the telescope schedule. Then you have a list of all completed observing periods, so you can look at how the time accounting is gone. So if you look at this first one here was scheduled for 3 hours. That's the duration, but it got billed for 0. The observations didn't happen. There's probably weather for these first couple. And then or there was something wrong with the telescope system. They all had to be rescheduled. Then you'll see observations that were fully successful after that. So that allows you to keep track of how the time's been allocated, where it's been, and also which days observations were successful, and so forth. So going further on down, if you do have a monitoring project, then we set windows. You will be guaranteed if you, excuse me, if you are given a guaranteed monitoring project, then we set up windows. You will be scheduled during one of these windows. So you can see the window start date and when the last date. So sometime in that time period, you will be scheduled. So it tells you what session, the start date, the end date, how much time it's going to be, and then how many hours have been billed and whether that observation is complete or not. Going on further down the page, you'll see that there are project notes and scheduler notes. So we can put notes in there. They're not typically used, so that other project team members can see those notes. The project abstract from your proposal and the disposition letter are put on this page. That's so you have easy reference to what those were in case you need to find it. And it's also any limitations or anything, requirements on the proposal that they need to know about. So moving on, you can make any changes to this DSS, or you can request any changes to these DSS parameters. We're happy to help you figure out what the appropriate changes are. However, you don't have control over all of those, so you need to make a request to me for those. You can also request that a new person be added to the project team. And as I said, just contact your project friend and myself, and we can work to make that happen. And so that's it. That's the DSS and a quick overview.
Thank you, virtual Tony. Does anyone have any other questions that they haven't put in the chat? There was one question about whether you will be scheduled in the Keyhole, and the answer came just a couple slides afterwards. There's that Keyhole parameter that can be set. And another about observer comments. So after you completely finish your project, we will send a notice to you that the project is complete, and there is a link for where you can put in any observing comments. This is helpful for us to let us know what went well with the project, what didn't go well with the project, and it can help us guide priorities and future work at the observatory. So please do fill out those observer comments. We don't have a really high success rate for comments that are submitted. Any other questions or comments from other Green Bank staff members? Oops. If not, we are going to finish a little bit early this session, and I'm putting in the chat again the link to the community Zoom. Jill mentioned that every 2 weeks, Green Bank has this community Zoom where it's another observer using Gbt data, telling a little bit about their work. And there's also an update about the current state of operations at the observatory led by Karen O'Neill. And so the link for registering for today's community Zoom, which begins in 13 minutes, is there. You're welcome to attend if you would like. You'll get an automatic link after you register. But otherwise, I will see you back here in an hour for our afternoon session. And we will begin with a little bit of more talk on proposal submission for the GBT.
Hey, Will, before you take off, I just had I'm supposed to help moderate Natalie's community Zoom thing, but it's not letting me in. So I don't know if you get it, if you have any access to that. I can send Paul Folstein an email or whatever.
I do not. Yeah, Paul would be the best.
Okay.
He might have to open it first. It might not be open yet.
Yeah. Okay.
I can send you the link that I have, but it's not the
No, I have that link too. So,
Okay.
Well, the system sent me a link, but yeah, okay, never mind. I'll send an email to Paul. I thought maybe you might be better, more powerful than I on this.
I have the login information, but I think if we use that login information, it shuts down the session and starts a new one. So we don't want to do that.
That's right. I've done that by mistake before. Never mind. Okay, I'll see you.
All right.